Hello, and welcome back to Unconventional Computing, CS492 in fall 2024 at KAIST. We're in chapter 2 talking about asymptotic computing, where asymptotic means that the model of computation involves some kind of infinity. And this is not unusual, since also the Turing machine involves some infinity, namely an infinite tape for storage. And this is a good approximation of actual digital computers because actual computers have finite storage, but very large storage memory. So a Turing machine with its infinite memory is an infinite model of computation, but a good approximation to actual finite digital computers. And we have started talking about other models of infinitary computation, particularly accelerating Turing machines. That is, computers that can make maybe 1 billion steps in the first second and 2 billion steps in the next half second and 4 billion steps in the next quarter second. So they keep accelerating. And this is kind of a exceeding version of Moore's law that computers actually do accelerate, but by proceeding to different technology, and also the rate of acceleration in Moore's law is considered fixed, whereas we consider also the rate of acceleration to accelerate. And these are the so-called Zeno machines. Zeno machines, right, so here's the recap. Accelerating named after Zeno's paradox, where the Achille, the fastest runner in Athens, takes less and less time to cover, but also to cover smaller and smaller intervals. And we discussed one possible way of realizing such Zeno machines, namely using relativistic computation, making use of the time dilation, time difference. Clocks run at different speeds for one clock of an outside observer compared to a clock of an object falling into such a black hole. Now, it seems it would be all. So this is an example of accelerating computation, relativistic Zeno machine. It seems actually reasonable way of harnessing this power of special relativity, general relativity, by taking the computer whose termination we want to decide, like an instance of the halting problem, running the simulation on such a digital computer, equip it with, let's say, such an atomic battery, which lasts almost infinitely long, and then throw that computer into the black hole and program in such a way that for the outside observer, the computer will send a light ray as a signal if it terminates, when it terminates, whereas if it doesn't terminate, then it doesn't send such a light signal. And because of the time dilation, there's an infinite time passing for the clock of the PC, when only a finite time, maybe 2 hours or 2 weeks, pass for the outside observer. And that would actually be almost practical because we have a black hole not too far from here in the center of our galaxy. But unfortunately, this is not how relativity theory works. It works the other way around. Namely, an infinite amount of time passes for the outside of an observer when there's a finite amount of time passing for the object falling into the black hole. So in order to use this to realize such kind of relativistic Zeno machines, we need to switch places. The PC whose termination we want to decide is the one that stays outside of the black hole, and the observer wants to know whether the PC terminates or not, is the one that who has to go inside the black hole. And this is maybe not so practical, because what happens when you fall into a black hole has been depicted, although artistically, by Disney. There's a movie from 1979, The Black Hole. So last time I promised you to show you an excerpt from that video, and this is what's going to happen now. I'm going to stop the screen share and switch to a different screen. So black hole is something very dangerous to fall into. You wouldn't want to do that, basically. Nevertheless, it is a way of realizing Zeno machines, of realizing accelerating computation that can make an infinite number of steps in finite time. And when we talk about such computation, then we need to clarify some notions, some ambiguity. Maybe what about the result of such a computation, right? Because such a non-terminating computation can change its output, can kind of change its mind, and this increases its computational power. So previously, we have considered many ways of solving a decision problem, such as, for example, the undecidable Holder problem, one-sided answers only, yes only, or other-sided answers, no answers only. Always correct, that's our goal, or correct at least infinitely often, or strong notion, correct, incorrect only finitely often. But these different types of concepts of computing, of solving a decision problem, always revolved around terminating computation. The algorithm stops, and the answer that is on the screen then must be yes or no. No other answer is permitted. And then this is then the definite answer, right? But if we consider non-terminating algorithms that don't stop, then they can also keep changing their answer. They can revise their output. First, the output may be yes, and then they change their mind and delete preliminary output, revert it, and write no. But they could keep on reverting yes and no. So that's a question of how to define. We won't allow computation that keeps changing its mind infinitely often, even among those computations that run for infinite time. We will accept only finitely often changing their mind, finitely revising, because infinitely often revising corresponds to paradox in philosophy about Thomson's lamp, which also keeps changing its state from being turned on to turned off, turned on to turned off, faster and faster, accelerating switches so that after two time steps, it is switched off and on infinitely often. And the philosophical paradoxical question is, what is the brightness of Thomson's lamp after 2 units of time? And that's a paradoxical answer. There is no right answer to that. Unlike Zeno, because Zeno not only decreases the uh, time difference between adjacent steps, but also the magnitude, the amplitude of these steps. So after two amounts of time, Zeno will be arrived either way. But Thomson's lamp, that question makes no sense. And similarly, the output of an algorithm that infinitely often keeps changing its mind, doesn't make sense. So we need to prohibit it. And actually, we consider variance algorithms that change their mind infinitely often are prohibited, but changing their mind once or twice or finitely often, that is fine. And we've discussed the computational power of a non-terminating algorithm, which may change its output precisely once or precisely twice. And we've seen that changing the output precisely once or precisely twice or precisely three times does not give more computational power because we can simulate it by an algorithm that terminates, that waits for one or for two or three output revisions, and then simply stops. Don't wait for further revisions because we've been promised to make precisely once or precisely two or precisely three revisions. And also, the essence is because we promised to make precisely two revisions, for example, then our simulation can safely wait for that second revision to happen. And it will happen because we have been promised so. So being allowed to make precisely one or twice or three times does not give more computational power to non-terminating algorithm compared to traditional terminating algorithms. However, when we allow an algorithm to make at most one revision, zero or one revision, then such a simulation by a terminating algorithm does not work because a terminating algorithm waiting for that revision to happen, but it may never happen because in condition B, we allow for at most one revision. So that means that simulating algorithm will never terminate and will not be a terminating algorithm. We cannot simulate an algorithm allowed for at most one revision by a terminating algorithm. And indeed, we've seen such a non-terminating algorithm able to decide the halting problem by first simply outputting no, it doesn't terminate, and then start simulating the input algorithm. And if and when the input algorithm terminates, then change its output from no to yes. And that happens at most once. The change in its output may happen 0 times. If the simulated algorithm does not terminate, then the initial tentative output no will remain forever. And similarly, such an algorithm can decide the complement of the halting problem by first outputting yes and then starting the simulation. Similarly, allowing a non-terminating algorithm to make two revisions also produces more computational power than allowing at most one revision. And allowing for at most three revisions gives more power than allowing for at most two revisions, and allowing an undetermined but finite number of revisions is more powerful than allowing for any fixed number of revisions. And the computational power of such a non-terminating algorithm allowed to make up to k revisions has been characterized by Joseph Schoenfeld. This is a classical theorem. Historically, it's called a lemma, but it's a theorem in traditional computability theory, one of the topics that I cover in my shameless cross-promoted class, CS422 theory of computation. And Schoenfeld's lemma states that a non-stopping algorithm allowed to revise its output at most k times, not exactly, but at most k times, is equivalent to a terminating algorithm, a stopping algorithm, which is allowed to make k queries to the halting oracle. So it may ask, the halting oracle may come up with the source code of some other algorithm and ask the halting oracle whether this other algorithm will terminate or not. Then it can come up with create a different source code of a different algorithm and may ask the oracle whether this one terminates or not. and it may do that up to k times. And the concept of oracle computation was actually introduced by Alan Turing in his PhD thesis, which is very well readable even nowadays. And of course, the terminology of oracle is a very strange one. It alludes to the old Greek oracle in Delphi, which was once asked by Alexander the Great, what happens if he goes at war? And the oracle answered, in that case, a great empire will fall. And Alexander thought this empire the falling empire was going to be the one he attacks. But it turned out that it was his own empire's demise that he initiated with this attack. And thus the answer of the oracle was ambiguous. Arguably, it was deliberately ambiguous. Anyway, so oracle computation as a way of completely characterizing the power of non-terminating revising computation, another model of non-unconventional computation, which has been considered in theoretical computer science for many years, and which can or cannot be realized using relativistic Zeno machines, but at the cost of a human sacrifice. Your professor may need to jump into the black hole to find out the answer. Oh, anyway, just kidding. So, with that being said, and another cross promotion to the very well readable book by Schoenfield, Introductory Book on Mathematical Logic, which can be read by every student of mathematics, really. Let's move on and now discuss another case, another example of asymptotic computation, namely using comb oracles. Comb oracle is a different kind of oracle. It's a mechanical oracle. And we start by showing you a finite mechanical comb oracle. So nothing infinite here for now. And here you see simply such a comb. And let's enumerate the pins of that comb, 1, 2, 3, and so on. And let's break off some of these pins, shall we? So here, some pins have been removed, and that is to indicate a subset or a decision problem for these natural numbers. Namely, 1 is an element of this comb, 2 and 3 have been removed as elements. No, only 2 has been removed. 3 and 4 are still present. 5 and 6 are absent. 7, 8, 9 are present. 10 is absent, and so on. Or in mathematical terminology, 1 is an element of that comb, 2 is not, 3 and 4 are, 5 and 6 are not, and so on. So in this way, the finite comb represents a decision problem, finite decision problem, because we have only finitely many teeth here, and we can mechanically, so this is about mechanical computer, we can mechanically solve these decision problems by probing whether the corresponding position in the comb, the pin, is still present or not. Here you see such a probe, right? A wedge, which can be moved to check, pin number 2 is absent. The wedge moves into that position. So in this way, a mechanical computer can find out whether the pin is present or not by sensing whether there's an obstacle when moving the probe, the wedge, into that position or not. That's a finite mechanical comb oracle. And now we're going to make the step transition from finite to infinite. Okay, so now we proceed to a comb with infinitely many teeth. And this is called Zeno's comb, right? So yeah, named after Zeno again. Zeno's comb is a comb with infinitely many teeth or tines, as it's technically called. And this is a case of an asymptotic oracle because of this infinitely. So here you see example. I try to draw it in my computer, one example of Zeno's comb. And you see that here in Zeno's comb, the tines, the teeth, become thinner and thinner, right? So the first are still pretty thick, but the next one becomes thinner and thinner, and they become thinner so fast in such a way such that infinitely many teeth fit into the finite length of Zeno's comb. Okay, and so roughly 1 over n squared, for example, will do. And so here we have a comb with infinitely many tines. And again, we can use that wedge in a mechanical computer to check whether the tine is present or absent at a certain position in that comb. The wedge is infinitely sharp here, and it just moves in a little bit to check whether these very thin tines are present or absent. You see here, this part is like Tom's teeth. This is an approximation. This is why it's an asymptotic oracle, right? Like Zeno's rays. And now let's consider a particular case of Zeno's comb, namely where the presence and absence of teeth encodes the answers to the halting problem. So previously, we considered a special comb with one present, two absent, three and four present, and so on. And now we moved on to a different comb with one present if one is an element of natural number, two present or absent, depending on whether two is an element of this halting oracle or not, and so on. And so in this way, we can encode the infinite halting problem as a subset of natural numbers into one Zeno's comb. We can actually encode any fixed decision problem into a different Zeno's comb. And then a mechanical computer can use that to probe this infinite comb in order to solve that decision problem, the halting problem, or any other decision problem. So that's another example of infinitary computation, namely with an infinite mechanical oracle, specifically a Zeno's comb type oracle. Now, is this realistic? Can this be approximated at least by an actual physical device? Well, there are limitations to that, right? We cannot make comb more thin than the width of an atom, okay? So that's one limitation. But that's a pretty large number, so it's Zeno's comb, which has as many teeth as there are atoms that fit into, let's say, one comb length. That's a pretty large number. But the problem with making this into a practical, powerful computer is a different way, maybe how to create such a Zeno's comb. If we get such a Zeno comb that contains all the answers to the halting problem up to, let's say, n equal 2 to the 20 or 2 to the 30, which is certainly possible with the atomic length, right? That would be very helpful. But how to produce this? In order to produce it in the first place, we may need to solve the halting problem first, and then use these answers to the halting problem for a machine, maybe some atomic force microscope, moving atoms in place to create such a Zeno's comb. But there's another option, maybe some alien technology provides us with such a Zeno scope, right? Then we don't need to create one, but we still need to verify whether the purported alien xenoscope is really a xenoscope for the halting problem, or is it a xenoscope for some other problem? Anyway, so this is another example of unconventional mechanical computation, asymptotic computation, using a xenoscope to answer undecidable decision problems. And now we're moving on. Our next part is about optical computing. Now we talked about optical computing, have we? Right, about solitary computing. But this is different. This is different optical computing. But before we start talking about this different kind of optical computing, we need to take away a lesson from the Xenoscope. And that lesson is about when we theoretically construct some optical computer, maybe using mirrors. We're actually going to use mirrors to construct an optical computer. Then the mirrors angles and normal vectors and positions of the mirrors cannot be arbitrary real numbers. They should be so-called computable real numbers. So let's talk a little bit for one slide about computable and uncomputable real numbers. So in Xenoscope, we discussed how to encode an infinite decision problem of natural numbers into one mechanical device, into one code. A different way of encoding such an infinite decision problem, it can be encoded into one real number, namely using the binary expansion of that real number. So for example, this example of Zeno's comp with 1 in, 2 out, 3 and 4 in can be encoded as a real number whose binary extension is 0 point. It always starts with 0.1 because this is in the comp, followed by 0, binary digit 0, followed by binary digit 1, 1, 0, 0, and so on. So binary encoding yields a real number starting with 0 point and then a sequence of zeros and 1, each one indicating whether the corresponding natural number is in or out of the set of the comb corresponding to 0 or 1 in the binary expansion. And here you see the formula for that, where C is the comb set and N is a position. And if N is in the set, then add 2 to the minus N, which corresponds to binary digit 1 at position N, and corresponding to binary digit 0 at that position. So this is how we can encode infinitary decision problems into real numbers. And of course, we can do the same trick with Zeno's comb, also with Zeno real numbers, by encoding an undecidable decision problem into such a real number. This is going to be called an uncomputable real number. A real number whose binary expansion comes from an undecidable decision problem. We won't want to use these in the sequel when creating optical computers, because that's already something we've covered here. For example, we could also consider a needle, right? A needle whose length is an uncomputable real number. And then probing the length of that needle instead of probing Zeno's comb allows the mechanical computer to solve an undecidable problem. And we've done that, we've been there, and now we want to move on and only consider computable real numbers and optical computers with computable angles of mirrors. So here's the formal definition of what we allow and what we prohibit. We allow only computable real numbers when creating optical computers in the next part. And a computable real number is one which has a decidable binary expansion. Uncomputable real number is one which has an undecidable binary expansion, such as one coming from the holding problem. And here's some examples or some facts about computable and uncomputable real numbers. There are uncomputable real numbers. For example, the encoding the halting problem in binary is an uncomputable real number. There's the famous Chaitin omega constant, which is an uncomputable real number. Every rational number, every fraction can be shown to be computable. I won't prove that to you here. That's something we can do in my other course. And there's some nice closure property, namely, if a real number R is computable, then also the sine of R is computable, the cosine of R is computable, the tangents of R is computable, and the inverse trigonometric function, the arcus tangents, for example, of R, is computable. And why is that nice? Because when we talk about angles of, let's say, a mirror, and we can either say an angle in multiples of pi, or we can talk about the normal vector, the direction of that mirror. And geometrically, the relation between the normal vector of a mirror and the angle of a mirror is given by these trigonometric functions, turning normal vectors into angles, and the opposite direction is given by the inverse trigonometric functions, converting angles into normal vectors. And this item B of the fact says we are only interested in computable angles or computable normal vectors. That's the same, because we can proceed back and forth without leaving the realm of computability. If we have an uncomputable angle, and corresponds to an uncomputable normal vector, and vice versa. If we have a computable angle, then it corresponds to a computable normal vector. And that's all preliminary consideration. And now we're ready to talk about geometric optics. And we'll see that this is reversible. And we'll make sure and pay attention that in the computer we're going to construct, a geometric optic computer as powerful as a Turing machine, that this computer, the mirrors in this computer are only computable at computable coordinates and point into computable directions or computable angles, which is the same as we saw from the last slide. So here's an example. Here's a mirror, and this one is harmless. It's simply a plain mirror. So its angle is 0, and its normal is just upward. And its coordinates are also at rational coordinates, so nothing to worry about here. And just a reminder for you from basic physics, when there's an incoming light ray, then it gets reflected when hitting that mirror, and the incoming angle, let's call it alpha, is the same as the angle of the outgoing light ray. So the light ray gets reflected and leaves at the very same angle as the incoming angle. This is sometimes called the law of reflection. There's also another optical effect that we're going to use, and that is not reflection, but action. The light ray enters some object which is non-opaque. Light can pass through that object. So here comes the light ray, and then again we have the normal vector, and the light ray is not reflected, this is not a mirror, but it enters the medium, but at a different angle. So when the incoming light ray comes in like from air or vacuum at angle A, then inside the medium it proceeds at a different angle, beta, and the relation between alpha and beta is given, remember optics, given by Snell's law. Snell's law says the relation between the sine of alpha and the sine of beta is given by the refraction indices of the air and of the medium. the incoming refraction index and the outgoing refraction index. That's Snell's law. And you know all this, at least qualitatively, maybe not quantitatively. Maybe if you put a stick into a lake, then the stick appears to be bent at the surface of the lake. It enters the lake at one angle, and it looks like inside the lake it proceeds in a different at a different angle, like it has been bent, and that's a result of the light rays actually being bent according to Snell's law. We're also going to look at another special kind of mirror that's a parabolic mirror. So here we have a plane mirror. Here we have a plane refractive object like water here and air here in the lake, or glass here and water here. And this is geometric optics. Why do I call it geometric optics? Because again, this is an as idealization. Actual optics does not act in that way for various reasons. Actual optics involves so-called aberrations, that means deviation from this ideal behavior. And these deviations are commonly characterized or classified as different kinds. One common aberration is chromatic. Chromatic means that refraction depends not only on the refraction index, but also on the color of the light entering and leaving. You might note that if you have to wear glasses like me, then the producers of such a glass go at great efforts to compensate for all chromatic aberrations, because otherwise you're going to see rainbows at every corner of every object, which is kind of psychedelic, but not desirable. So producer of glasses, Angyong, go at great effort to compensate chromatic aberration, but it's never going to be perfect. And we suppose in geometric optics that there is no chromatic aberration happening at all, which is an idealization. Another idealization that we consider in this chapter is that there's no defocusing of the light ray. So the light ray here is considered to enter infinitely thin and still powerful, and to leave here at the same intensity. Same here, going in and leaving at the same intensity, no attenuation, no defocusing, which is an idealization. In practice, of course, there's always lack of intensity, there's always defocusing, there's always attenuation. We also suppose that the optical controls are ideal, that there's no so-called coma, like perfectly planar mirrors here, perfectly planar surface here, and perfectly homogeneous water here, for example. And the final important aberration, deviation that we ignore here is the quantum mechanical deviations, wave particle effects. You may know that light is composed from photons, and when a photon hits some object, it transfers actually some impact on that object. Also, light is also simultaneously a wave, so particle and wave. And as a wave, it creates interference with itself, standing waves. And yeah, that's a famous experiment to create self interference of light to the wave effect. And this is again something that we ignore here in this topic called geometric optics. And as I mentioned, geometric optics is reversible. So if we change the order of the light, outgoing into incoming and incoming to outgoing, apart from these arrows to being misplaced, this is also going to be optical behavior. Same for refraction here. Okay, so geometric optics is reversible, and that's something we also need to keep in mind when we try to create optical computer. But now another brief interruption. for video on photonic computing before we proceed and present our own construction of a photonic computer. So I'm gonna stop the screen here and switch on